Okay, so we talk about Euclidean algorithm or Euclid algorithm, which is basically the method to find the GCD. Okay, so in the previous lecture we have seen this theorem or this result. If you have two integer a b, let a and b be any two integer, then we have seen this result GCD of a b is equal to GCD of a mod b comma b. So, this is basically gives us the what is called a Euclid algorithm to find the GCD. So, we will use this theorem or this result to have a algorithm. So, let us take an example. Suppose you want to find the GCD of say 24, 32. So, this is basically GCD of 24, then 32 mod 24 from this theorem. Now, 32 mod 24 means if we divides 32 by 24, then the remainder is basically 32 mod 24. So, this is basically how much? This is 8. So, because 24 is basically 32 is basically 24 plus 8. So, 1 into 24 plus 8. So, this is Q, this is R, the remainder. So, this is basically GCD of 24 comma 8. Okay. So, again this we can just GCD of AB is basically GCD of BA, we can just take it there, and then we can just or just we can say this 8 24 mod 8. Now, 24 mod 8 means basically 0 because 8 divides 24. So, this is basically GCD of 8 comma 0. So, GCD of a comma 0 is basically a. So, this is basically 8. So, 8 is the GCD of 24 and 32. So, this is basically what is called Euclid algorithm. So, we will write in a formal way. So, basically we will keep on calculating the remainder and until it's converts to 0, then it will give us the previous one will give us the GCD of AB. So, let us write this in an algorithm form. So, this is the Euclid algo. So, it has two input, which is basically two integer a and b, and the output will be their GCD of AB, which we can store in some number. Okay. So, this is the input output, and what is the code? We set this, we take b to be positive. So, if b is negative, we set this to be positive. Then while b is greater than 0, we keep on doing this, set c is equal to b, and we set b is equal to a mod b, and we set a is equal to c. So, this is the code for finding the GCD. So, basically this is a while loop, and this will execute until the b is not becoming 0. Okay. So, we can think for some recursive version of this. Recursive version is basically that formula Euclid. So, Euclid AB is basically this is the recursive call of this is this is the if b is equal to 0, then return a as a GCD. Basically, GCD of AB we are going to find out. So, instead of Euclid, we can just write that as GCD, the name of the algorithm, but algorithm is Euclid. Okay. Else if b is greater than 0, what we do? We return, this is the recursive call, return a comma or a mod b comma b, sorry, a comma a mod b. Okay. So, basically we will just sorry, b comma a mod b, this is the b part. So, this is the recursive call anyway, but this is the code. So, it is coming from that theorem that GCD of AB is equal to GCD of a comma a mod b comma b. Okay. So, now we will, before going to extended Euclidean algorithm, which is basically give us this theorem. Theorem means so GCD of AB can be written as AX plus BY, where x and y are some integer. And this theorem will prove, but this theorem will prove, but this theorem is basically give us the what is called extended Euclidean algorithm, finding the inverse mod something, modulus inverse. So, what is the modulus inverse? Further we need to know the modulus arithmetic. So, before that let us, so this is basically we will prove this theorem. This is basically coming from the Euclid algorithm, what we are doing, the remainder. So, basically to in the Euclid algorithm, we produces a sequence of remainder. Remainder R0, R1, R2 and so on, where R0 is equal to A mod B, R1 is equal to B mod R0, R2 is equal to R0 mod R1, like this. So, basically we continue this until we get Rn is not equal to 0. So, Rn plus 1 is basically Rn minus 1 mod Rn. Now, if Rn plus 1 is 0, then this Rn is basically the GCD of AB. Then Rn is basically GCD of A comma B. So, this is the way we find the GCD using the Euclid algorithm based on the theorem. Okay. So, now we will talk about modular arithmetic or the congruence relations between two integer a b. Modular arithmetic or congruence relation between two integer a b. Okay, let us take an integer n. Let n be an integer. It could be positive, it could be negative. And let us let I be the set of all possible integer. This is the integer set of integer. This we denote by capital I. Okay. Now, if you take any integer a, now we try to divide this a by n, then we get a remainder. Now, if you take another integer b, we try to divide b by, so this is basically remainder is a mod n, and if you take another integer b and if you try to divide b by this integer n, so that will give us b mod n. So, if these two are same, if a mod b is equal to b mod n, then we say that a b are related. This is the relation we are defining, and this relation is congruent relation, and this relation is denoted by this symbol. Then we say a b are related. This a b belongs to R, we say a is congruent to b mod n. So, that means this is a relation basically. So, that means a is related with b if we try to divide a by n, the remainder we get. If we try to divide b by n, the remainder we will get is same. So, for example, if n is equal to say 7 or say n is equal to 8. Okay. Now, if you take a is equal to 2, sorry, if we take n is equal to say a is equal to 10, and if we take b is equal to say 18. Okay. Then we can say, then what is a mod 8? It is basically 2, which is same as 18 mod 8. So, that means these two are related. This 10 is congruent to 18 mod 8. So, that means this 10 and 18 are related under this relation. So, this relation is defined as a is congruent to b mod n. Okay. So, now we will show that this is an equivalence relation. This relation is having some property. It is reflexive, symmetric, transitivity. So, what is reflexive property of a relation? So, this congruence relation is a equivalence relation. So, for that we need to show the three result. It must be reflexive. Reflexive means, so a must be related with a. So, a must be congruent to a mod n. This is quite obvious, because if we divide a by n, the remainder is same as if we divide a by n. So, this is quite obvious, nothing to prove here. Okay. Now, second property is symmetric. Symmetric means a relation R is called symmetric if a b belongs to R. This is a relation R. R is the real number set also. So, we denote by rho relation. Then if this imply B A is rho, rho is the relation, that means A rho B, if this imply B rho A. Anyway, R is here, rho is basically this symbol. So, this means symmetric means if A is congruent to B mod n, then this imply B is also congruent to. This is also quite obvious, nothing to prove here, because basically A mod n the remainder is same as B mod n, the both ways. So, this is also done. Now, the third property is transitivity. Transitivity. So, this relation is transitive relation, that means, if A is congruent to B mod n and B is congruent to C mod n, then we have to show that A is congruent to C mod n. So, this should imply A is congruent to C mod n. If this is true for all ABC, then we call this relation is transitive relation. So, is this true? Yeah, this is true, because from here we can say A mod n is basically equal to B mod n, and from here we can say B mod n is equal to C mod n. So, from these two we can say A mod n is equal to C mod n. So, that means A is congruent to C mod n. So, this is the this is the transitivity property. So, then since these three results tell us this is an equivalence relation. Equivalence relation over the set of integer. So, now we know, I mean, this is a result from algebra. If we have a equivalence relations, then it will partition the sets into the equivalence classes. So, that in each class the elements are related with each other. So, basically this will partition the set. Our set is the set of integers. So, this is the integer set I, and this is an equivalence relation, just now we have seen. This is an equivalence relation mod p mod n. So, n is the, so this n we can just write anyway. So, this is mod n. So, this will partition the integer set into the equivalence classes, disjoint partition, okay, dot 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 disjoint partition, and this partitions is in each of this partition, in each of this class, these are called equivalence class. If A, B are related under this relation mod n, then they are in the same class, then they are in the same class. So, now if so this class are basically denoted by 0, 1, 2 up to n minus 1. Okay. So, 0 class means all the integers, if we divide by n, its remainder gives us 0. That means all the integers multiply. So, 0 class means this set n, 2n, 3n plus minus like this. So, that means 2n is congruent to 3n mod n. So, that means they are in the they are related. So, that means 2n is related with 3n, because 2n, if we divide 2n by n, then the remainder is 0, and if we divide 3n by n, then also the remainder is 0. So, they are in the same class, and that class we denote by 0, because remainder sense remainder is 0. So, similarly, this one class, the remainder is 1. So, n, n plus 1, 2n plus 1, 3n plus 1 like this. So, these are the all integers which belongs to one class, that means remainder is 1. So, if you take any integer, so they are related. So, they are basically, so 2n plus 1 is congruent to 3n plus 1 mod n. because their remainder is same. So, 2n plus 1 mod n is 1, 3n plus n mod n is 1. So, remainder is 1. So, that is why this class is denoted by class 1 in the remainder sense. So, that is the reason. So, if we divide any integer by n, the remainder will be either 0, 1, 2 up to n minus 1. So, that is the reason we call this set up to define this set up to n minus 1. So, these are the, so any integer will be fall one of this class. Okay. So, this set is basically denoted by Zn. This set is basically denoted by Zn. So, we denote Zn by this set 0, 1 up to this classes, equivalence classes. For the simplicity, we just write this 1 to up to n minus 1. This is denoted by Zn. So, this is basically set of all equivalence classes. So, that means any integer will belongs to one of this class. So, if you take any integer a, now if you take mod n, so it will belongs to Zn. So, remainder will be either one of this 0 to m minus 1. Okay. Now, let us take an example. Suppose we take say n is equal to 6. Okay. Then what is Zn? Zn is basically 0 class, 1 class, 2 class, 3 class, 4 class, 5 class. So, that means any integer if you take, if we divide by 6, it will be remainder will be either one of this integer. So, it will be any one of this class. Okay. Now, we will define a addition on this set, this Zn. So, how we can define addition on Zn? Suppose we take 2 element from Zn, R and S, let R and S from Zn. So, we define, so basically we can write this by this sense. For simplicity, we are just writing this 0, 1, 2. So, then we define class as, so we just take the R plus S mod n box. So, if you take R plus S mod n, so it will be again in Zn, it will be from 0 to n minus 1. Okay. So, this is the plus operation we defined over Zn. So, basically for simplicity, so if a b coming from Zn, then we define a plus b is basically a plus b mod n. So, that means it will be one of this. Okay. So, then we can show that this will form a group, this Zn along with this plus will form a group, Zn comma this is a group, not only group, it is a cyclic group, and this is number of elements are finite. So, this is an example of finite group. So, how to prove this is a group? So, for a group we need to have few properties like closure property, which can be easily shown. So, a plus, so if you take 2 element from this, if you take 2 element a b from Zn, then the closure property is a plus b is also in Zn, the plus, the way plus we have defined. Then associativity is also true, a plus b plus c is equal to a plus b plus c, we can easily check that, and the existence of identity element. So, identity element is basically 0. So, a plus 0 is basically a is equal to 0 plus a. So, this is the identity element, existence of inverse. So, for each, for a we have minus a. So, minus a again is, so minus a mod n. So, a plus or minus a is equal to 0. Okay. So, for then, So, this will form a group, not only group, it is a abelian group. That means, A plus B is also equal to B plus A. It is a abelian group. Okay. So, now we just take an example. Suppose we take this Z6. Z6 is basically 1, 3, 4, 5. Okay. So, now, so the closure property is satisfied if you take any two elements. So, basically say 3 plus 5, how we define this is basically 3 plus 5 mod 6. So, this is 8. So, this is basically 8 mod 6, this is basically 2, which is belongs to Z6. So, closure property satisfy. Similarly, we can show that associativity is also satisfying. Then 0 is there. So, if you take any element, so 3 plus 0 is 3, any element plus 0 is 0. Now, the inverse. So, what is the inverse of minus 3? So, minus 3 is basically, so minus 3 is basically, so 3 plus of minus 3 should give us 0. Okay. So, it is in mod 6 operation. So, so minus 3 is basically plus 3, because if we take 3 plus 3 is 6. So, 6 mod 6 is basically 0. So, 3 minus 3 is basically 6. Now, what is the minus 4? So, 4 plus of minus 4 should give us 0. Okay. Now, so basically minus 4 is 2, because so 4 plus 2 is basically 6. Now, 6 mod 6 is basically 0. It is giving the, so operation is the as if our real number addition, but under modulo 6 operation, under mod 6 operation. So, this will form a, so this 2 is served as the minus 4, 2 is the additive inverse of 4. So, like this. So, this is every element has a inverse, and this is a abelian group, and so this is a finite group, because there are only 6 elements, and this is a cyclic group. So, who is the generator for this? So, we can check that 1 is the generator, because 1, if we 1 plus 1 will give us 2, 1 plus 1 plus 1 will give us 3, like this. So, 1 plus 1 plus 1 plus 1 4, 1 plus 1 plus 1 plus 1 plus 1 5, then 1 plus 1 plus 6, then mod 6 is basically 0. So, 1 is generating all the elements. So, 1 is the primitive element. So, we will check whether this is the additive sense. We defined the addition over this set. Now, we will talk about the multiplicative sense, whether it is a group under multiplicative sense or not. So, that we will talk about, and we will see in general in the multiplicative sense Zn is not a group. So, we will see that. Thank you.